Hi, everybody. Welcome back to Dave's Math channel. And today I'm going to talk about an important topic in math called symmetry. And I think most of you know what symmetry is, or at least you're familiar with certain types of symmetry. The most well-known type of symmetry is called bilateral symmetry, or more simply mirror symmetry. And if you look at these pictures, each of these pictures here has mirror symmetry, just the lines shown on the diagrams are axes of mirror symmetry, also known as bilateral symmetry. Um, anyway, so you're probably familiar with that. And I guess in terms of aesthetics, bilateral symmetry, almost all animals have it, and particularly butterflies. There's a picture of a butterfly, and butterfly has very close to perfect bilateral symmetry about its body. You have two wings that look almost exactly the same on both sides, as well as his body. And most people think that people with bilaterally symmetric faces are more attractive than those without. And this is kind of interesting. I just ran across this picture. These are pictures of Ben Affleck. I guess somebody ran a mirror or a mirror image through the middle of his face, and the picture on the left looks like a mirror image of both sides of, I guess, the right side. I'm not sure if it's the right side or the left side of his face, but one or the other, and the other is the other one. And it looks like one side of his face is bigger than the other side. And I don't know if these pictures look better than him. I don't think they do. But anyway, we do like people who have pretty close to bilaterally symmetric faces for some reason. Um, so symmetry is aesthetically pleasing, but there's not just bilateral symmetry. There's a lot of other types of symmetry. A starfish, for instance, has what's known as fivefold symmetry. This is rotational symmetry. It still has bilateral symmetry, but it has more symmetries than that. So if you notice that if you rotate a starfish 72 degrees, one-fifth of a circle, it still looks the same. Um, so anyway, that's another type of symmetry known as rotational symmetry. And you don't have to have bilateral symmetry to have rotational symmetry. The starfish has both. But if you look at the flower in the middle, the purple flower, you notice that the petals are not symmetric. So this actually would look different from its mirror image. So it does have a fivefold symmetry, but it does not have bilateral symmetry. And if you look at the hexagon on the right, this one has both bilateral symmetry and sixfold symmetry. So you can have a lot of different symmetries. And a circle has all these symmetries plus a lot more. A circle, it turns out, has complete rotational symmetry, meaning that you can rotate at any angle you want about the center and still looks the same. So circle has a lot more symmetry than any of the other things I've shown you. But these are just mirror symmetries and rotational symmetries. There's other types of symmetry as well. There's what's called translational symmetry. It turns out a honeycomb has also another symmetry known as translational symmetry. Note that it's made of hexagons, so like a hexagon, it has bilateral symmetry and sixfold symmetry. But not only that, notice that the honeybee can move from any of these hexagonal honeycomb regions to another one, and it looks exactly the same if he moves. That's called a translational symmetry. And this is known as a lattice. Lattices are like regular arrays of points, like a honeycomb, that have translational symmetry. And then this next picture is what's known as wallpaper symmetry. It turns out that there are 17 of these groups. I'm not going to talk about group theory in this video, but there are 17 different types of wallpaper patterns, it turns out. And interestingly, this was known for a long time. This was actually discovered by, I think, the Spanish in the 14th century when they designed the Alhambra, a very famous old temple in Spain. I've been there; it's a beautiful temple. But they exhausted all these possibilities. So if you go to the Alhambra, you'll see every one of these 17 wallpaper patterns is a different pattern of stained glass. And I don't think it was mathematically proven that there were just 17 until the 19th century, but the Spanish discovered it by exhausting all the possibilities, which I think is kind of interesting. And then, yeah, then and so far I've only been talking about 2 dimensions, but we don't have to stop at 2 dimensions. We can go to 3 dimensions, and these five figures here, what are known as the five platonic solids. They're named Platonic because the first person who studied them was the ancient Greek philosopher Plato, who was also a mathematician, and he discovered all five of these. The tetrahedron, that's the one on the upper left. It's kind of a three-dimensional analog of an equilateral triangle. And then I guess I don't know why they do these in this particular order. If you look at the bottom middle, that's the cube. That's the one most people know about. Then you got more complicated ones. The upper right is called the octahedron. And the names kind of refer to how many faces they have. Tetra means four. So a tetrahedron has four faces. Cube, also known as a hexahedron, has six. Octahedron has eight. The one with the next number of sides, next bigger is the dodecahedron. That's a figure with 12 faces, and they're all pentagonal. And then the icosahedron has 20 faces. And so, anyway, these five platonic solids, it turns out, are the only five solids in which every face and every vertex looks the same. And that's a symmetry. That's a three-dimensional rotational symmetry that each of these five platonic solids have. And you don't have to just stop at solids. You can go to the sphere. And like a circle has complete twofold rotational symmetry, two-dimensional rotational symmetry. Sphere has complete three-dimensional rotational symmetry. There's actually 3 degrees of freedom of how you can rotate a sphere. And so, but with a circle, there's only one. So you can do a lot of rotations on a sphere and everything looks the same, which is kind of cool, I think. And like with translational symmetry, there is a three-dimensional analog of that as well. These are what are known as the Bravais lattices. These are all. I think there's seven. I don't know. Maybe there's their mirror images as well. But I always learned that there were seven different Bravais lattices. They're showing 14 of them here. Maybe they include the mirror images. But anyway, if you want to know the analogs of the wallpaper groups. Remember I said there were 17 wallpaper groups? Well, if you go to 3 dimensions, these are what are known as the crystallographic space groups. And it turns out there's 230 of them. I don't know who classified them all. I think it was a big, huge task to do so. But anyway, we know that there's exactly 230 crystallographic space groups, in case you're interested in that. And I'm going to finish by talking about what I think is really cool. This is what's called the Penrose tiling. And this not only has, notice it has fivefold symmetry. That's pretty obvious. If you rotate it 72 degrees, it looks the same. But not only does it have that, it almost has perfect translational symmetry. Not quite. It turns out that there is no possible lattice in 2 or 3 dimensions with fivefold symmetry. That's pretty easy to prove. But it turns out that the Penrose tiling is the next best thing. This was discovered by a very famous mathematician and physicist named Roger Penrose in 1974. It's an example of what's called an aperiodic tiling. It never quite repeats, but actually gets very, very close. It gets arbitrarily close to repeating. And one reason this thing is really fascinating, it turns out that there are analogs of the Penrose tilings in 3 dimensions. They're called quasi-crystals. These were discovered by a guy named Dan Sheckman in 1982. And it was really a mystery when he first discovered them because he found that there were these substances that had, X-ray diffraction patterns with fivefold symmetry. And he didn't know what to make of that at first because it was long known that there's no crystals with fivefold symmetry, so it couldn't be a crystal. But it turned out it was a three-dimensional analog of the Penrose tiling, which was known. So I think finally by 1984, Sheckman figured out what was going on, and he realized that these were, sort of three-dimensional quasi-periodic structures, also known as quasi-crystals. So anyway, that's my talk on symmetry. I hope you enjoyed it, and I'll see you next time.